Right, so the last chapter we're going to look at, chapter 11, is on sequences and series. Okay, the first section, sequences, basically we're going to look at different types of sequences, finding patterns. A series, very similar to a sequence, except you add up all the numbers in the sequence, and that gives you a series. So a series is basically a sum. And then later in the week we'll look at some other things we can do with what's called the binomial theorem, and how we can come up with a quick way to FOIL things out. Really, really fast way. Much faster than FOIL, especially when you have to do lots and lots of multiplying. So it's basically the three things we're going to look at. All right, so first of all, a sequence is a set of numbers with a specific order. When we name a sequence, we usually use a lowercase letter. Any lowercase letter is fine. And then to identify a term in the sequence, you use the name of the sequence and then a subscript with the position you want to know. So the first term in sequence B is called B sub 1. The second term in sequence B is B sub 2. B sub 3, B sub 4, all the way up to B sub n. Some sequences are infinite, meaning they go on forever. Some are finite, which means they stop. Okay, I'll define both those terms in a second. Okay, any question on how you name a sequence or reference a term in the sequence? Okay. So for a sequence to be uniquely determined, there must be some kind of rule or formula to calculate the terms in the sequence. Right, so let's take a look at this sequence. 2, 5, 8, 11, ... There's an nth term, and then there's a ... after that, which means this sequence never ends. It just keeps going. Okay, anyone think they could give me a formula if these are the positions? First, second, third, fourth term, nth term. Somehow I want to figure out a formula for the terms in that sequence. And there's actually two formulas. A little different. Yep?
N minus 1.
Yep, you could take a sub n minus 1 means to take the term before the one you want. And what would you do with it?
Add 3.
Add 3. Perfect. Okay. That's one type of formula. I'll tell you the name of that in a little bit. Can anybody think of the disadvantage if I say asked for the 20th term? You'd have to find the 19th term. But then what would you have to do to find the 19th term? Find the 18th term. And to find that one, the 17th. So the disadvantage to this kind of formula is you have to find every term up to the one you want. There's another way to do it. Does anyone see a different formula based on the term number? Some arithmetic you can do with the term number to get the actual term. Give you a hint, it has to do with tripling the term. Yeah? Yes. Here's another formula that says to find the nth term, take 3n minus 1. So if you want the fourth term, 3 times 4 is 12, minus 1 is 11. Third term, 3 times 3 is 9, minus 1 is 8. The advantage of this second one is that I could find any term I want, and I don't need to know the ones before it. So if you said, what's the, 1,000th term? It's 3 times 1,000, which is 3,000 minus 1. 2,999. So very, very quick. So we like working with the second type of formula more than the first, but we will work with both. All right, so any function that you can come up with, okay? Basically, think of something like this. Let's say 4x plus 1. If you take that function and you limit the domain to just the positive integers, meaning you limit what you plug in for x to be numbers like 1, 2, 3, 4, you have a sequence. Okay? The reason you have to limit it to positive integers is because with a sequence, you have a first term and you have a second term. There's nothing between them. There's no such thing as a 1.3 term or 1.5 term. Okay? So if you just limit yourself to integers, you would have a sequence. And you'd rewrite it. Usually we use this notation where n is any positive integer. So any question on the connection between a function and a sequence? A sequence is just a function limited to positive integers for the domain. That's all. Okay, an infinite sequence, that's a sequence where the numbers that you plug in for n, right there, can go as high as you want. The domain is all positive integers. A finite sequence, it's a subset, meaning it's only part of the positive integers. It's some of them, not all of them. So usually you start at 1, and then you would end at a certain value. Okay, so in my example, I said I'm going to go from 1, 2, 3, all the way up to n, where n is some positive fixed number. Okay? Maybe n is 10. Right? So if n were 10, that means in this finite sequence, it would consist of 10 terms. Right? Let's say in this one we did, let's not go all the way to 10, let's go 5. It's a finite sequence because I'm not going to infinity, I'm stopping at 5. So I can find the first 5 terms. Okay. What is the first term here?
5.
Yep, 4 times 1 is 4, plus 1 is 5. Second term? Third term? Fourth term? And fifth term? 21. And that's the entire sequence. Okay, that's a finite sequence. Any question on the difference between a finite sequence and an infinite sequence? So as I said, tomorrow we'll talk about adding up all the terms in a sequence. For a finite sequence, you can always add up all the terms. Always. Because there's a certain number of things and you can add them all up. What would be hard about that with an infinite sequence? Yep.
It goes on forever, so you can't add it up.
Right. You can't actually add up infinitely many terms. Okay. And for this kind of sequence, if you were to go on forever and just keep adding these numbers up, what would your answer approach? It would approach infinity. So for an arithmetic sequence, or that's what we're going to call it, this kind of sequence, we usually don't add up infinitely many terms. But for a geometric sequence, which I think Corey mentioned earlier, you can. Okay? Here's an example of a geometric sequence. What's happening to my terms each time? They're getting smaller and smaller. I'm dividing by 2 each time. So if you think about adding up infinitely many terms, eventually the terms are getting so small, they really don't make a difference anymore. That's kind of how you can think about it. So it is possible to add up infinitely many things and actually get an answer, or get something that gets closer and closer to an answer. Right, but we won't look at that till tomorrow. Right, let's just practice listing the first 3 terms of this sequence. Okay, a sub n equals n squared minus 1 divided by n. Okay, to find the first term of that sequence, I would plug in what number for n? 1. If you plug 1 in the numerator, what do you get?
0.
Yep, 1 squared minus 1 is 0. And what's 0 divided by 1?
0.
0. Yep. What if you plug 2 in? What do you get in the numerator? 3. And in the denominator?
2,
2. Okay. What if you plug in 3 in the numerator?
8.
8 divided by
3.
3. Yep. And those are the first 3 terms of that sequence. Any questions on that?
All
right? Oh, sorry, the first three terms and the 15th term. Okay, what's 15 squared?
225.
Minus 1
225.
divided by 15. Does anybody notice what the fraction is getting closer and closer to each time? So the first one is 0. That one doesn't really help. But the next one is 1.5. 8/3 is 2.6 repeating. 224 over 15 is 14.9, roughly. So,
Oh, it's getting closer to the denominator.
and the denominator is the term you're looking for. So as you get higher and higher, like if we were to do the 200th term, I bet the answer would be very close to 200. Right? It would be 200 squared minus 1 divided by 200. Okay? So it's approaching the term number. Okay, let's try this one. This is going to have really different behavior. What do you think is going to happen here, especially with this negative 1 to the n? What's that going to cause our sequence to do? All right, we're going to definitely have big gaps between the numbers. I mean, can you be more specific?
Well, the even exponent to be positive and the odd exponent to be negative.
Right. Anytime you have a negative 1 to the n in your sequence, or any negative number to a power, it's going to cause your sequence to oscillate. Positive, negative, every other term. Okay, and this 2 to the n is going to cause things to double. So the number is going to double each time in the sequence, but it's also going to switch signs. Okay, so what would my first term be? It would be, start with negative 1 to what power? 1, and then times 2 to the 1, which is?
Negative 2.
Negative 2. Okay, now the second one, it's going to be negative 1 squared times 2 squared. 4. So notice it doubled and it changed signs. So what's b cubed? I'm sorry, what's b sub 3? Yep, negative 8. And b to the 15th, you could do the pattern out or just plug in the 15 for n. What's negative 1 to the 15th? Negative what?
Negative 1.
Yep. And then 2 to the 15th, that's 32,768.
Negative 32,768.
And then when we multiply by negative 1, okay, any questions on that one? Okay, so that's what a negative 1 to a power does. Causes things to oscillate positive, negative. If you tried to graph that, you wouldn't see any picture on your calculator because you can't raise negative 1 to a decimal power. It's not possible because you would get imaginary numbers. Right? So if you type in negative 1, just put it in parentheses. Always have to put it in parentheses. Times 2 to the x. Look at your table. Okay, first term is negative 2. That's what we said. Second term, positive 4. Third term is negative 8. 15th term, negative 32,768. Now try 1.5. It says error. And the reason you're getting an error is not because of this part. You can raise 2 to the 1.5 power. That's fine. It's the negative 1 raised to the 1.5 power. Okay, it's not a real answer. It's imaginary. Any question on that?
Why is it imaginary?
Why is it imaginary? Because if you think, what's 1.5 as a fraction? 3 over 2. So what I'm trying to do is take the square root of negative 1 cubed. What's negative 1 cubed?
Negative 1.
Negative 1, and the square root of negative 1 is I. So actually, if I put my calculator in imaginary, let's see if we get I as the answer when we do -1 to the 1.5. Negative I. Well, we were close. So -1 to the 3/2 is, I'd have to think about why it's negative I and not I. Unless,
Negative imaginary number work.
you know what, unless you think of it this way.
Itself out to make it positive.
Okay, think of -1 cubed is -1 squared times -1, and then you can pull out a -1 squared. You know what I mean? Because when you square and square root, they cancel, and the -1 comes out. That's why. Okay, I'm not sure if there's certain decimals that you might be able to do it with. For example, if you had a fraction with an odd numerator and an odd denominator, you can take an odd root of a negative number. That's fine. So let's think, how about like, let's try 4/5. Okay, because that's taking a 5th root. That might work. What's 4/5 as a decimal? Yep, that works fine. Okay, so basically, if you could write your exponent as a fraction and the denominator comes out odd, you can take odd roots, no problem. You just can't do even roots.
They can't do -1 to the 1/4 power.
-1 to the 1/4. Nope, that wouldn't work.
Because it's
Nope, you can try it, but it won't work. It would be, see how it's imaginary?
okay.
Okay. If I left my calculator in real, it would have just said
It's an
error. Yeah. Okay, so it's kind of weird. The exponents you can do and the exponents you can't do, but that's why it comes out imaginary. All right, so because the sequence is a function, basically, just limiting the domain to integers, we can graph it. Right? When you graph it, what do you think it would look like if you're limiting yourself to just integers? It's not going to be a connected line.
It's going to be like the steps.
This is just going to be dots.
Yeah, it's just going to be whatever the pattern is. It could be a curve or a line, but it's just going to be dots. That's all that the picture would look like. So let's try to graph the sequence we just had. Okay. Does anybody remember what the first term was in this sequence?
0.
0. And the second term?
3/2.
Third term?
8/3.
Thirds. And let's do one more. Fourth term?
You got me there.
15.
And now we'll graph them. So the first term is 0. The second term, 1.5. Let's make it a little bigger. Third term is 8/3, which is 2.6 repeating. So notice, and I'm trying to show each time I graph a dot, it's getting closer and closer to that next number. 15/4. 3.75. Oops. So 1, 2, 3.75. Okay. Any questions on that? So that's it. That's how you graph a sequence. Just don't connect it, okay? Because there's nothing in between the dots. Right, so there's two kinds of formulas we can work with. Okay? And you guys gave me an example of each with the very first problem. There's an explicit formula, which is the kind of formula we like to work with because it allows you to directly calculate any term you want in the sequence without having to find what comes before it. Okay. The other type of formula is a recursive formula. And in general, it can be pretty hard to change a recursive formula into an explicit formula. I'm going to give you some to do, but they're going to be easy. So in a recursive formula, what they generally do is they'll give you the first term, or sometimes even the first couple terms in a sequence. And then the rule is going to be based on adding or maybe multiplying the term before the one you want to get the next term. Okay, and there's a famous sequence we'll talk about in a minute where you need to know the first two terms in the sequence, and you add them together to get the next term. Does anybody know what sequence that is?
It's like the 1, 1, 2, 3, out.
Yep, 1, 1, 2, 3, the name of that one.
I don't know what it's called now.
Begins with an F. Fibonacci. So Fibonacci sequence is basically a sequence where you take two terms, you add them together, and that gives you the next term. There is an explicit formula for the Fibonacci sequence, but it's very difficult. It's not something we're going to study.
Can you show us?
Honestly, I don't remember it. I studied it in grad school, but it was pretty complex. It was really complicated to figure out.
Kind of goes with his name, Fibonacci.
All right, so here's an example of a recursive sequence. Anytime you see a sub n minus 1, that means it's recursive. You're doing something to the term before the one you want in order to figure out the pattern. Right? So what is this formula basically saying to do in words? If I want to know a given term, how do I find it? What does that box tell me to do?
Add 3 to the previous term.
Yeah, add 3 to the one before it. So what would a sub 2 be?
5,
And a sub 3?
8.
8. Okay, not bad if you just have to find a couple terms, but certainly we would want to do this for very high numbers of terms. Okay, any question on the difference between explicit and recursive?
What does the whole an minus 1, is that just the subscript for the first, for whatever number is in the sequence?
It's the term minus the thing.
A sub n minus 1 is the term before a sub n.
Oh, okay.
So if you wanted to think about it,
So if you did.
here's a sub n. Here's a sub n minus 1. This is a sub n minus 2. A sub n minus 3. And then if you wanted to go after a sub n, what would it be? Plus 1. Okay, any questions on that? All right. So looking at this formula, is this a recursive formula or explicit?
Recursive.
It's recursive. Okay, it says take the term before the one you want and add 4 to it. Okay, so we're going to find the first 4 terms and the 8th term. But since we're doing it recursively, what does that mean we really have to do?
Okay.
We got to really do all 8. Even though they don't want the 5th, 6th, and 7th, we need to do them. Okay, what's the first term here?
2.
Yep, 2. That's given. Second term?
6,
6. Third term?
10,
10. Fourth?
14,
15.
18, 22, 26.
30. So they wanted the first 4 and the 8th term. Any questions on finding the terms in a sequence given a recursive formula? All right, so this time I've given you a recursive formula, I've given you the first term, and I want to see if you can convert it to an explicit formula. Okay. Whenever you just have a previous term plus or minus a number, it's super easy to convert it to explicit. If you start getting into formulas like take 3 times the term that's 2 before the one you want, plus 4 times the term before the one you want. Now this starts getting a little harder. Okay, this is the kind of stuff that can take a really, really long time. So we're not going to get into it. Not bad to calculate terms. You could do that arithmetic out. Not so easy to change to explicit. Okay, what's my second term here?
8.
Yep, it's going to be 8. And how about my third term? 13. Okay, so these are the term numbers. First term, second, third. Anybody see an explicit pattern here? And I'll give you a hint. It's going to have something to do with 5. And then maybe adding or subtracting something.
5 times -2.
All right, let's write it down and then let's check it. Take 5 times the term you want and subtract 2. 5 times 3 is 15 minus 2. 5 times 2 is 10. Take away 2 is 8. Yep, seems to work. And we're going to do 2 things. First thing I'm going to do at the end of class is show you how you can figure this formula out without even really thinking about it. Just by knowing the first term and that number. Those are the only 2 things you need to know. And the second thing we're going to do, not this academic week, but next academic week, is we're going to prove that that's the formula. Okay? Now we've shown that it works for these 3 cases. I could show it works for 100 more cases, but that doesn't actually prove it. Right? So we'll talk a little bit about proofs in the last 2 days of class. Last 2 days next academic week. All right, so this sequence that we're going to look at is called the Fibonacci sequence. If you Google it, you'll find all kinds of things about Fibonacci. Tons of uses for this sequence. And this sequence is a little different than the other ones because it doesn't depend on just the first term. You need the first 2. So the first term is 1, second term is 1. And somebody explain to me in words how you get the next term knowing the previous 2. How do you get the next term in the sequence knowing the ones before it? You add them together. Take the 2 previous terms and add them up. So what would a sub 3 be?
2.
Yep, 2. My next term?
3.
5. And that's the first 6 terms. 1, 1, 2, 3, 5, 8. Again, we're not going to find an explicit formula for this, not in this class. Any questions on that one? Okay. So I want to take a look at this triangle for a second. You might want to draw the first 3 or 4 rows, just so you can see the pattern. But no, you don't have to do it all the way out past row 4. Okay, one thing to notice here is the counting is a little tricky. They start with row 0. So we have row 0 going down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Row 13, that's the last row. And this triangle has a name. Does anyone know the name?
Fibonacci period.
What's that?
The Fibonacci period.
We're going to talk about there's a connection between the Fibonacci numbers and this triangle. You probably won't see it, but I'm going to show you. But it begins with a P.
Does that do Pythagoras?
Nope.
One more letter. Pascal.
Pascal's triangle. This is Pascal's triangle. Many, many, many different uses. You could probably write a book of things you can do with Pascal's triangle. All kinds of stuff. I'll show you a couple of them. First one I'm going to show you is how the Fibonacci numbers are hidden. Does anybody see where they're hidden? It's kind of tricky. But the Fibonacci numbers are in that triangle. Okay, these red lines will help give you a hint.
Interruption.
All right, so take a look at these red diagonals. And watch what happens if I position them right there. Does that give you a hint as to where the Fibonacci numbers are?
Around the outer two rows?
Not quite. Okay, I want you to look at those hexagons and look where the red line goes through the middle of a hexagon. What number does the first red line go right through the middle of? 1. Okay, how about the second red line? Another 1. Now what about the third red line? It goes through a 1 and a 1, which is a 2. Okay. What about the fourth red line? What numbers does it go through? 2 and 1, which adds up to 3. So if you add up the numbers that are cut right in the middle by the red lines, you get a Fibonacci sequence. Okay, that's just one interesting pattern here. Okay, another thing that comes up is if you look at, let's look at row 2. Ignore the 1s. Okay, so don't really focus on these. If you look at row 2, all the numbers are what? A multiple of what number? 2. How about row 3? 3. How about row 4? Yeah, and so they're not multiples of 4, but they are multiples of 2. How about row 5?
5.
There happened again, multiples of 5. Are row 6 multiples of 6? No.
Multiples of 3.
Yeah, multiples of,
Can't do 20.
not even multiples of 3. How about row 7?
Yeah, 7.
So what row number was a multiple of itself? What rows did it work on?
The odd ones.
It worked on row 2 though, right? So it worked on 2
The prime numbers.
prime numbers. If you take any prime number, that row will be multiples of that prime number. So row 11, all the numbers are multiples of 11. Row 13, all multiples of 13. Okay, interesting pattern. You could look at more. And let's take a look at this. So that means to do this out. What do I get if I FOIL this? X squared plus 2xy, yep, plus y squared. What's the coefficient of x squared? 1. And then the coefficient of the xy?
2.
2. And the y squared? 1. We had a 1, a 2, and a 1. What was the exponent that I had originally on the parentheses? 2. Let's go look at row 2.
Look at that. It's in the
1, 2, 1. 1, 2, 1. So these numbers are very helpful if I want to multiply out a binomial. So if you wanted me to cube something, I could tell you that 1331 would be part of the answer. It's not the entire answer, but it is part of it. We still have to figure out how to get this, this, and that. Okay, so we're going to learn on Thursday how to use this triangle for the binomial theorem. Okay. And of course, there must be an even better way, because if you wanted to do something, say, to the 20th power, it's time-consuming to write out 20 rows of the triangle. So there's got to be a pattern to how these numbers are generated. I don't think we mentioned it, but does anybody see in the triangle how you generate a number in each row? Where the pattern comes from?
You just add 2 on it.
Yeah, you just add the two numbers above it, and that's how you get the number below. 10 and 5 is 15, 15 and 20 is 35, and so on. And you just put 1s on the outside. Okay, but there is a faster way than doing it out with that pattern. Does anyone have a question?
How long did it take him to develop that triangle?
When was it? I don't know how long it took him. I'm not sure exactly when either.
Like, that would be many years.
But I mean, it's a very simple pattern. You just take the two numbers above it.
The pattern, though.
Yeah, it's an interesting pattern.
And not overthink it.
And there's so many other things that he probably didn't even know when he made the triangle that are in here. And there's probably 100 other things I don't even know about patterns. But I tried to just show you 2 or 3 things that pop up here. All right, so one of the kinds of sequences that we've already studied, I just didn't name it, it's called an arithmetic sequence. Or you might also see arithmetic progression, means the same thing. And recursively, what an arithmetic sequence looks like is you take the term before the one you want and you add a number to it. So when you are repeatedly adding a number, that's arithmetic. 2, 4, 6, 8, 10, 12. That's an arithmetic sequence. I added 2 each time. Okay, the number that you add each time is called the common difference. Now, you might be like, well, wait, he just said you add a number. Why is it referred to as difference? Well, yeah, if you subtract 2 numbers that are next to each other, the one on the right minus the one on the left, you'll get the common difference. 10 minus 8 is 2. 8 minus 6, 2. 6 minus 4, 2. Okay, so the common difference is when you take a sub n plus 1 and subtract the term before it, a sub n. Right? And we can also come up with an explicit formula, and this is going to take pretty much all the thinking out of finding a pattern in an arithmetic sequence. All you need to know is the first term and the common difference. And there's your pattern. Okay, so what we'll do is we'll look at a sequence. I want to see if you can come up with the formula without using the shortcut. And then we'll try using the shortcut and see that it comes out the same. Okay, so again, for the next problem, you can write this down, but don't use it. Just try to figure it out in your head like we did before. All right, so here's a recursive formula. There's one thing missing, though, from it that if I didn't tell you this, you can't really do very much. What else do you need to know for example 6? Yeah, you've got to have the first term. So somebody pick our first term. 3? Let's do something other than 3, just because I have a 3. I don't want to confuse. Just pick anything that's not a multiple of 3. 2, sure. All right. So first term is 2. What would the second term be? 5. About the third term? 8. And now, without using the shortcut, does anybody see what the pattern would be? Something times n plus or minus something. Yep.
The term times
Term times
3 minus
3
1.
and minus 1. Yep. Now, that's just kind of reasoning it out in your head, kind of looking at what you added each time and looking for a pattern. Let's try it with the formula. It says to get the nth term, take the first term, which is how much? 2, plus n minus 1, times the common difference. What's the common difference here? 3. That's what you're adding each time. Now that doesn't look like what we have. But what could we do to make it look like that? Yep. Distribute the 3. And you'd get what? Yep, 3n minus 3. And lastly, what's 2 minus 3? So there's your formula without really having to try to figure it out in your head. This process makes it mechanical, I guess. You just plug in the first term, plug in D, and that's it. Okay, any questions on that one? All right, so that's finding an explicit formula given a recursive formula to start with. Let's try this one. The first 2 terms in an arithmetic sequence are given. Find the 5th term. Now, because they only want the 5th term, you could just figure out the pattern and do the pattern 3 more times. But if I said to find the 500th term, you're not going to want to do the pattern 500 times. So let's come up with the formula and then use the formula to find the fifth term. Great. So using our shortcut, somebody remind me how to do that? A sub n would equal
The first term.
the first term.
Negative
Yep.
plus
Plus
n minus 1
n minus 1. Good.
times 5. Oh, sorry. Yep.
So 5 is my common difference.
6.
6?
Yes.
You sure?
Negative 6. What? That's 6.
So yeah, look at negative 2. If you ever get stuck, take the term to the right, subtract the one to the left of it, and that becomes negative 2 plus 8, and the common difference is 6.
I don't see you guys talking, so
Nope, you were right. You tried. You got it.
I did.
So you just add 6 each time. All right, so what do I get when I simplify this?
What?
6n
Minus 14.
minus 14. Now I can find the fifth term using my formula. If I plug in 5 for n, what do I get? What is it? 30 minus 14, which is? Yep. So we got the 30 by doing 6 times 5 is 30. Take away 14. A sub 5 is 16. Any questions on that one? Okay, this one a little different. They're giving us the third term and the eighth term. But which term do you really need to have that's most important? First term. That's the one you need to know. But I've given you enough information. We should be able to figure it out. How can I figure out what's going on here, given that it's an arithmetic sequence? Well, what does arithmetic mean? To get from one term to the next, what are you doing each time? You're what?
Subtracting the same thing.
Subtracting the same thing each time or adding the same thing each time? In this case, what's it going to be? You're subtracting the same thing each time. So how could you figure out what you should subtract each time without trial and error?
Wasn't just the difference between the term and
Well, that's the start of it. Find the difference between the term on the right minus the term on the left. So 3 minus 13 is negative 10.
And then just divide it by the difference in the position.
Yeah, and divide it by like the difference or how many jumps you have to make. 1, 2, 3, 4. We need to divide that between 5 jumps. So yeah, negative 10 divided by 2 is negative 10 divided by 5 is negative 2. So 11, 9, 7, 5. So now if we subtract 2 to go to the right, what about to go to the left? 15, 17. There's your first term. So what would be my formula this time?
17.
Yep.
Plus times 2.
And my common difference is negative 2. You're adding negative 2. Okay, distribute out the negative 2. We're going to get negative 2n plus 2. So we get negative 2n plus 19. It's not wrong if you write 19 minus 2n. That's fine. Any question on finding an explicit sequence in this kind of case? All right. So the last sequence we're going to look at is a geometric progression, or geometric sequence. And in this kind of sequence, you multiply the previous term by something. So arithmetic you add, geometric you multiply. Okay, so an example of a geometric sequence is 2, 4, 8, 16, 32, 64, so on. I'm doubling each time. So recursively, that's what this formula would be. To get a term, take the term before it and multiply by r, okay, where r is the common ratio of the sequence. Okay, to find the common ratio, it's just like finding the common difference, except you divide instead of subtract. And let's look at the sequence I just mentioned. Take any term and divide by the one before it, and you're always going to get the same number in the sequence. What's 32 divided by 16? 2. 16 divided by 8? 2. You're always going to get 2. Anybody think they could tell me the formula for this sequence? Or at least what number do you think it has to do with? Yeah, it has to do with a 2. And if these are your positions, what would you do with the 2 and the position to get those numbers?
2 to the n.
Yeah, 2 to the n, exactly. 2 cubed gives me 8, that's the third position. 2 to the fourth gives me 16. 2 to the fifth gives me 32. There's your formula. But we're going to come up with a better way to get the formula, so we don't really have to guess or try to do too much reasoning with it. We just have to use this. A sub n equals a sub 1 times r to the n minus 1. So this is the explicit formula for a geometric sequence. Let's try it on the one I just wrote and see if we get 2 to the n. Okay. What's the first term in the sequence I had? 2 times, what's the common ratio? 2 to the n minus 1. Now, what I wrote there and what I have up above, these don't look the same. Anybody know how to simplify the one on the bottom to make it look like the one on the top? Think about you're multiplying things with the same base. So what's the rule when you have exponents and you multiply with the same base? Yep, you add the exponents. Well, what's the exponent on 2? It's a 1. So if you add your exponents, what's 1 plus n minus 1? Just n. The 1's cancel out. That's it. Any questions on that one? Right, we'll try another one, and then I'll show you one more where you might have to do a trick like this to combine things together. Okay, let's try to find the explicit formula for this geometric sequence. Okay, the key thing you need is the first term. Normally, just knowing 2 numbers isn't enough information to find a sequence, but this word right here gives it away. It says it's geometric. So what did you multiply 6 by to get 12? Negative 2. So if you multiply by negative 2 again, what would you get? Yep. And then if you did negative 2 again, and we could keep going higher and higher, but really we want to go back the other way. So divide by negative 2. And that will give you your first term. 3. So now the formula says a sub n equals the first term. Okay, what's the first term? 3 times, okay, find your common ratio. Take a term, divide by the one before it, negative 2. And what power do I raise to negative 2? 2. n minus 1. Now in that problem, that's all you can do. That's your final answer. But let's say you had something like this. Okay, this is totally separate, nothing to do with this problem. 8 times 2 to the n minus 1. What could you do to simplify that? Yep.
2 and 3 times 2 and minus 1.
Right, you can write those with the same base, and you get 2 to what power?
3 minus 7.
N plus 2. That's a much simpler way to write than what I have up above. Okay? When you do it, it kind of hides what the first term is. Okay? If you had a sequence, this shows the first term is 8. This kind of buries it into the expression, but that is more simplified. What if you had something like this? Anybody think of a way you can rewrite the number 6 with a 2 somehow? It doesn't have to be a power, it could just be a factor. Yeah, you could write it as 2 times 3, or I'm going to write 3 times 2. And now what's the exponent on that 2? 1? 3 times 2 to be. Okay. Again, I would argue that what I circled is a little bit more simplified than what I had, because it made the number in front smaller and it took away the minus 1 from the exponent. Okay. The only reason you might have to do that is if it's matching and you get that as an answer, and that's the choice listed. You just have to understand those are the same thing. Exactly the same thing. And you could always check it. Try plugging in the number 4 for n. Try it in the bottom, try it in the top. It'll come out the same. All right. So, any questions on explicit formula for geometric sequence? All right. So the homework tonight we'll just be practicing with sequences. Tomorrow we'll look at a series, which is adding up all the numbers in a sequence. Okay. And it's 1 through 7 odd, 9 to 13 odd, 14, that's the only even, 17 to 27 odd, and 31.